There are two types of access points: hardware and software. Hardware that you all have at home, possibly. Um, so one typical hardware access points is router at home or some other repeaters. If you have huge castles, one router, wireless router does not cover, then you need to have another repeater and repeater, wireless repeater. Anybody has a wireless repeaters at home set up? Oh, great. Oh, maybe it's cool, right? Alberto? Yeah, extender, yeah. Yeah. Oh, yeah, yeah. Um, and there is also software access points. Software access points that you can set up. If you have a network card, wireless network card, then you can set up access points. CloudTrack also possible. Can almost all the operating systems has that capabilities. For example, Linux, Ubuntu. If you have, then you can set up access points together with DHCP services. Uh, the following slides gives you some hint to set up access points on your Windows systems, Windows operating systems. I captured the screen that I set up this, but we will practice this at Tech Night. I'm going to defer all to Tech Nights. Reason for that is, from my experience, if I bring some hands-on to my regular classes, sometimes we cannot move forward because there are some other students needs to learn and hold off all the speed of my lecture. So we will defer all to the end of this semester. But those who wants to do, or those who are capable of following this, I tried to capture all possible things here. So you may be able to do that. Let's try to take a look so that those who are really interested in, I know some of you are really interested in when no, Lockheed Martin team comes here for recruits. One team, uh, the champion of our cyber scale competition during spring and summer, uh, will have a chance to give demo to the Lockheed Martin teams. They're going to give two demos, a physical demo, real doable demo here at the lab. If you are interested in, you can come back to the same day, but a few hours earlier. Lockheed Martin. On that, the regular sessions, they're going to give a presentation also uh, at the main hall, lecture hall, uh, where there might not be their own separate networks available. But here in this lab, we have independent, separate networks, independent from Mercy campus, so that they can maximize their implementation features. So that's what probably they need. If they set up, for example, software AP on one laptop uh, running over Windows, another laptop on Ubuntu, another laptop as a just a station, and do some uh, wireless packet uh, whatever that is, a cracking, right? Some wireless attack program. Um, so you will see that maybe in a couple of weeks. But today, I'm going to give you this is a detailed explanation, although we don't do real implementation here. You need to first take a look at network interface availability by typing, this is a Windows command, netshell. Is a very, very famous command in when you bring up your, for example, let me see if I can do. Yeah, Windows command, then you can simply type netshell wireless LAN and show drivers. So it'll show all the wireless LAN drivers. And we can pick one of those. What do we have? Yeah, this is a Broadcom. This is a wireless network card on my system. Once it is available, then we can set up access point host. This is another command with some options. Same command, netshell, but with different options. For wireless LAN, set hosted network. Hosted network. I believe this is a reserved word, hosted network. And mode equals allowed. This is attributes, so that you need to specify whether you want to allow or disallow. And SSID, service set ID, that you need to also name it. This is also reserved word. You cannot say anything else but allow or disallow. But SSID, you can name it. Okay, Alberto. Then there is Alberto SSID. And key equals whatever the key that you have, right? But these are all attributes is reserved word. WLAN, set, hosted network, and mode equal, SSID equal, key equals, those are all reserved word. So if I do that, as I did here, remember that I do here, and then everything looks okay. Okay. One thing that you need to make sure that this whole thing needs to be run as administrator. If you are not an administrator on your Windows systems like mine, how can you run your Windows command as an administrator? That's right. So I cannot. It's very simple. Start button, and there is a command prompt. Once you have that, it appears here, and then right click on it. Then there is a run as administrator. Once you run the Windows command as administrator, then you can run this. Okay.
Because at this point, you just running you're running an access point. You still need any connectivity if it isn't going to work.
For setup, right, administrator privileges required. If you do as a regular user, then it's not going to work.
As soon as it's set up, as soon as you feel something's over set up, you still need actually connectivity for order this to work.
For station, of course, you can. That is extra.
Yeah.
Right, from your cell phone can also access.
Yeah,
Right. Doesn't require. Only for setting up
right.
requires administrators. And next slide can tell you start. You can start this hosted network as I did here. If you have this prompt, it says a hosted network started, then yours is ready. But many times it's very hard to get, but sometimes you don't get it started. Once it is started, then you could see that SSID on your network and sharing center. Remember that you can get this network and sharing center from control panel and all, yeah, from control panel. Then you can see this. You have your own, for example, this is a Verizon and something else, right? Here is a wireless network. So what you need to do a little more is that you need to do a network configuration. You have your own network. This, for example, wireless network from this. This is from Verizon, so that you have a wireless network. You can clearly see this is a wireless network. Then you need to set this to share with your access points. So that you need to click the share tab and allow other network can come into your Verizon network. Okay. You can do it at home. If you ask that here, then we cannot move forward. All right. After this, if you do this, then what happens is that, for example, from your cell phone, you can see that access points, or from any of extra independent uh, uh, notebook can recognize it. Okay, that's what we will do next. And in real experiments, in our case, what we will do is, oh, this is another thing that we can do. SSID or SSID can be found. I think this is something that we all need to download. I want you to download SSID 4 from this website. I want you to do it right now, so that later, I think after the break, we'll launch this, and we all can see wireless signals and with the SSIDs. I'm not sure how powerfully it works here, but we'll try this. And Wireshark is another program that we can see, but you know this from many other courses, so I'm not going to repeat here. SSID? Oh, older version. I have an older version. Older version looks okay. Probably I can. Maybe I can be sued because it's a public. But if anyone has, yeah, then I can get you. Yeah. Another thing is that this is a recorded. It's very hard to get to this point and remove many times. So better not. Okay, we'll get back this by the time of our, yeah. So we can test other computer as a station to connect the software AP that you just set. We can try that. Okay. Do you have that USB? Anybody has an empty USB so that I can get you one? If yours is virus free. Okay, so once access point is ready for your client devices, then we can see the beacon, probe request, probe response, association request, reassociation request. All such things can be verified where, which, in what way? Let's say you have access points running on Windows and your smartphone and access to that. So you want to see all the possible packets. So beacon, that is one packet, comes into your access points so that you need to see it. Probe request, that can be Wireshark. Yeah, Wireshark can display it. So up to this point, we will do that. Okay, attack night. We'll defer all technical, detailed lab to the tech nights. Possibly by that time, we do not have enough time. I allocated 3 weeks for tech nights, right? What I want you to do, I mean, this course also requires a group project, right? So as a group, you need to pick some issue and some possible implementation, possible hands-on labs from my lecture when I introduce. And you need to figure out which hands-on technologies will be used for your group project.
Can you give an example?
There's so many examples that this is one example also. While to capture some, Wireshark itself cannot be a project. Right, that's too simple. But Wireshark is a tool for you to show something. Yeah, like this through the Wireshark, because you have already access points and stations. So you want to show how they are really associated with each other. That's what they can do, right? Association, reassociation. By looking at the packets. That's what I'm saying here. What do you found from all the steps here when you look at the old data that you can see from Wireshark? You need to analyze all bits and bytes. So why this bits set to 1 or set to 0? Some bits are very, very sensitive. Some bytes are very, very sensitive. Or many bytes are non-sensitive. They're just payload, for example. Well, payload is sometimes very, very sensitive if it contains password, right? All right, so that is the thing that you can do. Meanwhile, I'm going to copy some for you to install. If I have, I'm not sure if I. Infrastructure of, there are many ways that wireless communication can be set up and being operated in this infrastructure, of course, and some ad hoc, no infrastructure needed, right? If you have an infrastructure, then usually there is a service set. So multiple base stations in a service set possible. So each station in this case, that's an end node, your laptop, for example. Okay, there's no services, but only receiving services. So each station associates with one at a time, to one service at a time. Um, and base stations periodically send out, base station in this case means access point, for example. So access points periodically send out beacon. This is called the beacon. What it does is that it keeps saying that, oh, here I am. Anybody wants to associate. So SSID, one SSID that you name it, right? You can name, as I did, something, right? Which is nothing but a base station identifier. So each AP access point has its own SSID. So there is a probe packets, beacon packets sent from the access points. Then your station needs to probe the packets and back and forth. For example, probe two kinds: probe request and probe response. When you say, here I am, then you can say, oh, I want to talk to you. Probe request. Then I can say, oh, yeah, you can associate with me. That's what they do. For example, if you have a base station 1, base station 2, and 3, and base station 1 has this coverage, 2 has another coverage, and 3 has another coverage. Each base station set up a different number of channels and different capacities, right? And different multiplexing algorithms so that it can serve, for example, 10 users or 20 users. Usually there is a multiple of 2, right? Multiplication of 2. 2 users, 4 users, 8 users, 16 users, 32 users. Here in this Mao Hall, for example, at Mercy at Dobbsbury campus, there's an access points router available, but doesn't serve many subscribers. So that if you want to set up Wi-Fi from your cell phone, it tells you Wi-Fi is available, but actually you don't receive data especially from my office. I'm not sure here in this lab, but in my office, when I turn this on, Wi-Fi available, so that I probe all the verification done, so that I have that signal, wireless signals, but I don't receive any at all. So that, right, capacity issues. But anyway, so each base station has some coverages. Distance, of course, this, right? And also the channel capacities. How many channels, therefore, how many subscribers can be served. But you are not only at one place, you may move, because this is a mobile station. So you may move from the region of the base station to another coverage. Then very nicely switch over to another and another, right? So to do that, two things needs to be involved: physical layer and MAC layer. Those two layers are fully specified in the regulation 802.11, IEEE 802.11. So what MAC medium access control can do is uh, to transmit and receive data at reliable fashion and control access, of course. So some security issues and encryption issues involved. So in the next module is going to deal with wireless encryption algorithms. And protection of data. So it deals with noisy and unreliable mediums, frame exchange protocols. For example, if you have one data is being sent, therefore it should one data transmission requested from one station, for example, then it should occupy wireless channel. In other words, certain frequencies. So the frequency band needs to be shared. Not fully occupied. At some points, some wireless channels needs to be occupied for one data communications. If there is time-sensitive operation requires. It's not sharing with the others, but occupy one channel. Certain period of time. But other than that, we need to share. Therefore, acknowledgement is needed, which means if I'm done, then I need to say I'm done, right? That is acknowledgement. Question?
No, I was going to say, just like voice packets or session SIP packets, they have a rules for the service associated with them, where routers give them priority over other.
Oh yeah, which means yeah, that is yeah, point point coordinate function-based communication. Then, for example, access points, base station and station needs to talk point to point, right? Then it has a higher priority. How can we manage the higher priority? That will be discussed in the later slides. They're very smart. They're all controlling based upon time setting, timestamp. For example, this type of communication needs to wait this long time. Another type, at least wait this time. But if we compare these two time space, then this is shorter. That time critical services can wait only this shorter period. So while everybody waits at this side, but this guy can wait only this shorter, so that he has a higher priority. So he can take that channel. So the others, meanwhile, backed off and wait for another allocation. Right. So we have clear examples of that. I forgot to distribute homework assignments. I'll do that. Sorry, Jessica. Jessica wants to work during holidays, but so not only that, ACK acknowledgement. There's a similar other packets needed, RTS and CTS. What RTS and CTS stand for? Some of you might know, right, already. Anybody out there knows what RTS and CTS stands for? All for request to send, clear to send. Okay, that something like that. So this is part of the protocol, part of the handshaking between server and clients. When they want to occupy the channel, wireless channels, which means when they want to use a specific frequency band. While you are simply unknowingly use your smartphone, this kind of protocols is keep running very accurately, very nicely. Therefore, you do not have much difficulties, or you do not have much complaints, right? If sometimes they mix together, then you have a lot of interference and interruptions. But these days, we do not have such malfunctions in our wireless communications, right? But at home wireless communications, sometimes you may have some interferences, right? One device to another device. It's not working in 1 second, so they have to click one more time. Talib, while you were at the training, another thing that you might be interested in is wireless communication, the old fashion of wireless communications. Old fashion. That is LED based wireless communication. What is LED? Yeah, light, right? I mean LED, LED, some diode, right? Yeah. So that is that is I think 3.5 kilohertz. It has some frequencies generated. So LED lights, over the LED lights, we can carry some data. Think about the remote controller. Remote controller, if you see the remote controller, there is LED lights. It's not just the lights, but when you press some button, so predefined data is transmitted to your base station, whatever that is, a TV set, for example, right? So TV set receives through that carrier. What is the carrier? LED lights, and then split to receive data itself, and accordingly it reacts. There are a lot of security issues, right? For example, it is not, I mean, previously, and at home, LED-based wireless communications, there's no security protection at all because, for first of all, it's not that expensive, right? Secondly, only used for entertainment, at home only. But for example, if you have very famous guys uh, at what is that? Madison Square Garden. They rented it for $1 million, and you want, but you do not like that guy, so you can attack. All the wireless microphones are now under your control, not those guys. How about that? There's attack, right? Wireless attack. That cheap uh, environment, uh, there's no much security uh, control.
You're referring to like remote controls,
Everything, yeah,
robotic security, you can also cover that too.
correct, yeah. So you can think about that also. So let's look at a little more Mac. Mac has some counter. For example, a timer, time controls, depending upon the protocols. May have different time controllers. And CSMA CA is the major technique that we use. CSMA slash CA, there's an acronym uh, that you should all know about if something happens at your interviews. CSMA stands for? You're very good. Anybody wants to repeat what he says? Right. Carrier. Carrier is sensible, right? Carrier sense, multiple access, slash. Um, there is a collision. Remember that wired communications are very good at collision detection. Once collision is detected, then because that is a wired communication, always that they can uh, fix it. Correction is always possible. So detection mechanism well developed. But in wireless, um, basic assumption is that your station is moving from one location to another location. Therefore, access point is not the same access points as before. So all changes, right? So while you are still associating with a specific access points, you want to make sure that all transmission is accurate. So collision avoidance is very, very uh, applicable here. That is the reason that we use that. In order to this collision avoidance, a lot of times that we have to, some other signals needs to be backed off. While one signal is picked up for transmission, then all others needs to be on back off mode, which means it should wait, right? But there's a binary exponential back off, which means it's not really randomly, oh, you wait 1 minute, you wait 2 minutes or 3 minutes. It's not going to do that. It is randomly, but always multiplication of 2. 2 to the power 1 minute, 2 to the power 2, 2 to the power 3, 2 to the power 4, things like that. And wait. You may back off so often if you are unfortunate, right? So initially, for example, you can have earlier exponents, lower exponents, 2 to the power 0, so that you can wait only 1 second. And next time, maybe it may be increased. NAV, next network allocation vector. So depending upon this, network allocation vector is available on each station, at each station. Which means at each laptop, it has its own allocation vector. So it knows, oh, I need to wait and where possibly that I can get in. Something something to be known by each laptop, for example. To control all these concepts, there is a timing intervals. SIF, basic slot time. So if you set basic slot time, for example, 1 microsecond, then depending upon this slot time, for example, SIFS is double, or DIFS times 4, EIFS times something, PIFS something, right? There's an IFS. IFS stands for inter-frame space, in time, inter-frame space. For example, 1 frame moves, then you have to wait, for example, 2 frame, 2 inter-frame space, or 3 inter-frame space time, or 4 inter-frame space time. So rather than saying that numbers in this algorithm already set up, some interframe space, if it is small, we call that small interframe space. This is PCF-based interframe space, which means point coordinate function-based interframe space. This is a distributed coordinate based interframe space. So these two major coordinate functions based on P or D, P for peer-to-peer, D for distributed. Actually, DIFS is always available for anyone. On top of this DIFS, I mean DCF, D stands for DCF. DCF stands for distributed coordination function. It comes somewhere here, so don't worry about it. Where is it? Here. Distributed coordinate function and point coordinate function. Okay. Oh yeah, here. DCF and PCF operation. So DCF is always available. PCF is available when it comes to time-sensitive data to be transmitted. When it is time-sensitive? Time-sensitive means there is a deadline. Some control packets are time-sensitive, not the data itself. Some control packets. For example, the carrier company wants to make sure to monitor some, then they use this PCF usually, so that they can monitor some wireless networks. maybe some military, I do not know, but maybe so, right? Civilian, no. Medical, maybe. If they need to send time critical patient data from one hospital to another hospital, if a patient is the president of the United States, right? Or General Talib. Are going to be up to that level? Okay, so we'll get to this more detailed. Don't be frustrated on this slide. This slide is busy, right? Tells you so much, but you will see eventually, clearly, a little bit. Okay. Collision detection. Only one slide. And after, oh, this is another. Yeah, not many slides. Collision detection does not work, wireless, as I said already, right? But collision comes, two types of collisions. A send, A transmit to B so that B can hear, right? Well, but A does not know when there is a C also send signal to B. Then one signal comes here, another signal comes here at the same time, then there is a collision, right? For example, Alberto and me both try to talk to David. But I do not know Alberto is the other side of David. So does he not, right? So we talk, David, and he talks, David. It happens in our real life, right? If somebody talk and call him at the same time, then he's always, oh, which one, right? Same thing, right? In our daily life, we can simply resolve it, which one, like that. But in real data communication, there's a data collide, which means we don't have a data. Then there is a problem. Collision, we know there is a collision, but we cannot say, hey, resend, hey, resend. If it's a collide, then it's collide, which means we have to avoid it. Therefore, we need to make sure before we send, somehow myself and Dave needs to shake hands before he shake hands. He can shake, presumably he has only one hand. I do have only one. If he has two hands, then he can shake hands both. Cool. Right? That is not the case here in wireless, okay? He has one device, he has only one init, so that I can shake with him. Okay, now we talk. Because he knows, and I know, we can talk, we share that. We want to follow some protocols. So he's ready. Therefore, he would not accept another participations, right? There's a hidden cases. Another case is here. B send out the data to A, but this is wireless. So definitely C can hear it, right? Your data can be exposed to everyone. Of course, there may be some encryption and some access controls can be involved here, but forget about that. So communication itself, then there is a collision, right? This is another type of collision. So what do you need to do? If I want to talk to a specific participant that I need to first to shake hands. So here, CSMA does not work well for wireless here. C cannot know to wait until it can't hear carrier from A. B can hear both A and C, thus collision at B. A is hidden to C. This is the case of that. And another here. C here, C thinks it should wait since it can hear the carrier from B. If A is out of range C, then C waits needlessly and C exposed to B. Somehow we need to have this kind of protocols. How can we control that? To do that, we have these solutions: RTS, CTS, and ACK. Request to send, some type of communications protocol needs to be shared. Before I send, I need to say, I want to send it to you. There's a request to send. Then David said, okay, now clear. I do not have any other but you. Between you and me, there is a clear channel. So clear to send. If you share RTS and CTS both, then there is a data to be transmitted. So data can be transmitted. Finally, the recipient, if data completely received, the recipient acknowledge, hey, I received. Not completely, it's a packet, right? One packet, one frame. So one frame received. And there is also a mark, right? Usually CLC to verify integrity of data, then they have some redundant code. The example of that is a CLC, right? Cyclic redundant code, cyclic redundant check, right? Cyclic redundance check uses a few code at the end of the data, so they need to verify. Only by looking at the code, they can tell, oh, this is it, still preserve the integrity or not. So by up to that point, the recipient now know that, oh, I received the data. Then acknowledge back to the sender. So each packet contains, all packets contain address of the sender, address of a receiver, and some durations. So, again, for this, you can verify very clearly using Wireshark. Wireshark, then you can see the frame and all the information, all possible information contained in a frame called packet. Let's say you have A and C. You are here. This is you. B. B as a sender, B as a receiver. B as a sender and B as a receiver. Right? if you want to send, then you need to request to send to A. And then you know that you requested to send to A. Therefore, scenario is a little tricky, but we can think in this way, or 4 different players. Let's think of 4 different players. 4 different players. I think that is better. So we have 4 different players. Here's sender. Sender wants to send to A, then okay. Here's the thing. Between S and R, A and C are external. We have S and R, 2 different players. Sender wants to send signal to R. Before it sends, what he needs to do is to send the RTS packet to the receiver. Once a receiver think there's no other communication, then all respond with the CTS, so clear to send. After clear to send packet arrives at the sender side, then sender now send data. So keep sending the amount of data. Then finally receiver say acknowledgement. So this is the protocol. Similar things can be talked with the others. There's another communication with A and another communication with the C in this case. Access points, yeah, access points. It depends on who sends. For example, upload and download. If you want to upload, then your laptop is a sender and access point. At that scenario, right? Access point is a receiver. So access points receive the data when you upload, and then even forward to the other side. And if you want to download, then access point is the sender, and then your laptop is the receiver. So it takes turns. By having that, we can deal with a little bit of hidden terminal problem and exposed terminal problems that we looked at, right? What was the hidden terminal problems? When A sent to B, then C also sent to B. In order to avoid that, when A wants to send, A needs to say, hey, I'm ready to send. Then B needs to say back to A, clear to send. Therefore, C waits to send. C also here receives something, but well, thing is this: B first send the CTS to A, and then this CTS is a little later. After this guy do acknowledgement, or after this guy receives acknowledgement. Oh well, no. Well, after this data comes, and B needs to do ACK. After ACK, then B can come back to C. Okay, clear.
Does that
To
just
send.
the C? What if you already hit A is between A, B, C is 2? Does it keep communicating?
A and B, one packet done, then that is done. Then we need to switch to another packet to deal with between B and C. So A and B, there is one packet done, and another packet B between B and C, and then another packet again back to between A and B, possible. It's a packet by packet data piece. Similarly, we can do here. Yeah. So, for example, B wants to send particularly to A, but so RTS. But this is wireless communication, so RTS can be received by all surrounding. Not only A, but C also receives. But this guy is the only one which is waiting for this, so that this guy, okay, I'm clear. C does not know. If it receives, still do not know what's going on. So there's no clear to send the signal received by B. So B responded to this only. So data now send to data now send to A, and finally A acknowledge. Then C is completely um, excluded from that communication. Again, there is a security issues, encryption issues, cryptography, right? RTS is not really encrypted, but somehow access control needs to be involved. So this is similar to that, but in another. So what we now want to do is we need to get into deeper for that. Okay. 802.11 has both physical and virtual carrier sensing. Physical carrier sense can be by physical layer, which is the lowest layer, and virtual carrier sense provided by MAC layer, which is layer 2 in 7 OSI. And virtual carrier sensing, which is provided by MAC, maintains this network allocation vector. Network allocation vector needs to be maintained by each station. So each laptop has network allocation vector, so that he knows how many minutes wait, not really minute, how many microseconds wait, and what carrier needs to be, what sub-carrier needs to be in. NAV records a prediction of future traffic on medium. So some counter that counts down busy time at a uniform rate, and there is, based upon time counting, RTS and CTS can, those two packets can be transmitted in certain order. As far as um, some time space is set to non-zero number, then uh, carrier is still busy. So at my time, if there is uh, a zero vector, then I can send. I can be in that communication. So this explains a little bit about that. Here's a source. Here's a destination. Say this is a station 1. Destination is station 2 or access points. Doesn't matter. Anyway, station 2. And another station 3 and station 4 and station 5. There are many stations. Try to be using the same carrier. Okay. Then there's a time, DIFS, some time space. Depending upon the time unit, if it is a microsecond, then DIFS may be 4. SIFS, this is small, so maybe time unit, so 1. In this scenario, we have DIFS and SIFS only, right? DIFS and SIFS. So time runs in this way. So source waits DIFS time space. DIFS is in the distribution mode. Distribution coordination function based interframe space. That is the time, DIFS. So wait this long. And if this is my time, I want to talk to the destination, whatever the station it is, right? Then send the RTS if it is my time. And also, I am maintaining NAV, network allocation vector. So I know time, as time goes, I reduce the time. And by looking at this, oh, it's free, so that I can send the packet. But before I send the data, I need to send the packet of RTS first. Why? In order to avoid all collisions. So send the RTS. So RTS takes some time period, right? And then destination also waits some time. Although it receives at this time, SIFS, time needed. So interframe space, short interframe space, that much time needs to be waited. And after that, send out CTS. This CTS go back to this RTS, come back to destination, CTS go back to the source. When source when CTS received at the source side, then wait again, short interframe space. Because it receives and destination and channel is now clear to use, therefore sending data. This is data. Now data is sent. This data contains the like destination address, source address, and some other packing numbers, frame numbers, all information, all other information, including the payload. Okay, so send out, and it receives at the destination. But at the destination, we have to wait another small interframe space, and after that, send acknowledge. Once it is done, this one packet transmission is done. Then, as we did here, distributed coordination function based interframe space needs to be waited. See here? This, as we have here, we had here, right? So in this, while this is source and destinations are communicating, so all others defer access. So this guy needs to have some NAV, network allocation vectors. So this guy knows CTS, RTS. How? This still receives, right? This is not really point to point. This is wireless communication. If I am in that access points coverage, then my laptop can receive the same RTS as the destination receives. So by looking at that CTS RTS, we can maintain the number in that NAV. Increase, decrease, increase, decrease, and finally, oh, I maybe chip in. Okay. We can practice this by number, real number. So that is a simple algorithm, but that is everything. We keep using that, even if there is a complicated scenario. We still use RTS, CTS data and acknowledgement. RTS, CTS data and acknowledgement. In between, there's an interframe space needs to be used to wait. Interframe space, IFS. So channel access mechanism, there are two kinds of channel access mechanism as we looked at before. This is a distributed, this is a point. Point seldom implemented in practice. Usually you and I are in this function, distributed coordination function. Carrier sensor multiple access with the immediate MAC level acknowledgement. So there is a four-way handshaking. For example, what are four ways? RTS, CTS, data, and acknowledgement. Four ways in this way. For example, if you're a sender, and then you have a receiver, then sender first say request to send. Then receiver says CTS. One way, shake hand, first way, and second shake hands. And then third, we need to send the data. And finally, this guy says CK. So four-way, right? So very simple. this PCF is over distributed communications. It's not alone usually. TCF is running, and then PCF, upon needed, occupies. It's a higher priority. It's a contention-free period. If it is distributed, there is a contention, which means they need to compete each other. Your turn, my turn. Your turn, my turn. Right? PCF is contention-free. Already points are designated. So PCF can do some area contention free 4 and yeah, alternate with the DCF. It's running over DCF, but idea remains similar. Only the difference is the priority. In DCF, we can have this protocol CSMA/CA. There's a time period, DIFS, interframe space, if that is based on DCF, then usually 50 microsecond. 50 microsecond. But SIFS, usually 10 microsecond. We have multi each, and between the RTS, CTS data, there is a SIFS. Usually SIFS time period is 10 microsecond, which means short, right? DIFS 50 microsecond, much bigger than that. So during this time, if busy, then wait until it is not busy. So random back off. If not busy, then we can send. We can transmit. Transmit what? Packets in that order. RTS, CTS, data, and ACK. In that order. Back off, usually binary exponential. So 2 to the power x. Okay. Based on what? Some slot time, right? If this is a slot time, yes, then 10 microsecond. If slot time is half of this, 5 microsecond, then SIFS is doubled the slot time, and DIFS, for example, is times 10. In between, there is a PIFS. Point coordination function based IFS. Then there is in between, maybe 20 microsecond. Some station wants to do point. Everybody needs to wait this time period, DIFS. Should wait 50 microseconds. But there is one station, oh, I do PIFS. So before get to this 50 microsecond, only within 20 microseconds, jump into that communication. So there's a prioritized, right? Station 1 and Station 2 each has DAV, network allocation vector. Based upon network allocation vector, they know that, oh, now DIFS is ready. But if it is used by someone else, then they back off, random, whatever the time. This guy, well, Station 1 back off. Station 2 involved in, oh, they are talking each other. No.
So the nap time, if you exceed the nap time, it just keeps it active. Let's say because it's waiting, the nap time is waiting.
Right, wait period. If you are not in that communication, then you have to back off again. Yeah, longer time.
That
Yeah.
time is the backup time is the active.
Right. Yeah.
So what happens if you exceed that? It just won't send it back.
It reset again.
It restarts.
Yeah. If you are not picked up for this communication, then
So
reset
it'll
to
reset the packet.
right, reset to another time period and another time period. So at worst case, continually back off. At worst case. What does that mean to you? Your laptop is not connected. Sometimes you have that issue, right? Sometimes you don't have communication. All of a sudden, your NAV is infinity. So you have to be you have to reset. So fresh file, fresh.
You can only have a session with one laptop at a time.
Correct. Yeah, one laptop at a time for particular channel. But router has a multiple channels open. Yeah.
Even if it uses a single channel, it multiplexes packets.
Oh yeah. So they can time share. That's what we do here, time share. So multiple participants can share this time period by having that DIFS and all those SIFS and that scenario. This I'm occupying during that time period, and after that, some other station jump in, and some other station jump in.
Per channel. So one channel will not have a designated time. So your laptop will have a certain time.
Oh yeah. That is depending upon the packet data size of packet size. One packet needs to be completely sent out. One packet through that sequence, RTS, CTS, packet data, and acknowledge. But you have another packet, right? For example, you have previous size of documents to send out. Then it can be decomposed into multiple packets. So per each packet, it should be in this
So in that case,
protocol.
RTS and CTS at the same time.
RTS, CTS per channel.
Per channel.
Yeah, if you have another channel, then another RTS, CTS.
Like it would be to RTS that reply because it's
No, there's a sequence.
He's saying it's clear to send.
Yeah, RTS first, and then CTS needs to be replied.
So what happens if it's not clear to send?
Then wait.
It just waits.
Yeah, because there's no clear, right? That is the way that collision avoid protocols. For example, I want to send out. You all receives, but I want to send this data to whom? Abu, the father. You all receives, right? Abu also receives, but Abu says clear to send. Then I can send it, right? All others, because I don't receive any of you the CTS, so I don't send it to you.
So you broadcast RTS, the others you can communicate with this and that senses.
All broadcast because that is wireless. Yeah. But we know that when I send the RTS to everybody, then somebody replied with the CTS, then I know him. So that from that time, okay, this data is to him. But you all can receive, may be able to receive. But by that time, another thing is that then we can share the key, for example. Okay, if that is asymmetric key, then yeah, I can send the key back and forth. Okay, from this time, you can decrypt my data using this key, things like that. So that is coming next module.
So in theory, everyone can get or have access to the packet. So if you can capture that, you can hack that.
Of course, that's what. Yeah, all the time you may, if you can hear someone's data and voice, but uh, but but you cannot. Your device, your device does not capture it, does not receive it because
Just talk about cybersecurity.
according to the protocol, this is not the device that I send to.
It's open air. So
It's open air. Yeah, you can right. But each packet has sender address and receiver address. Um, if you set up INSSID then uh, all the wireless signals can be captured, so you can see it.
I get that. I was just talking to like cybersecurity. I was saying, if, I know if you take off, if you're able to capture information, you're able to use supercomputing. It's easier to crack if you can capture that and then use a supercomputer to crack it. That's what I was saying. If
Yeah,
you can capture that, even if you can capture the time and space, you can take that information and then later work with that with a
that's
fast
possible.
computer
Mhm.
and break that
Exactly.
eventually because I don't care what encryption you have, you have
Right,
computer
right.
power.
Eventually, right. Depending upon the computing power, it can be cracked in quick.
For 256 bits encryption, even with the supercomputer mainframe, you need 1,000 years or this is math. It's
No,
not
no, I got you.
thinking or not.
No. It's just
But if you're so lucky, um, how to share common channel? For example, this is very typical wired network, but similar to the wireless network as well. The theory that we can find from wired network can be applied to wireless by tuning a little bit. But all the ideas and problems that occur wired, same thing wireless. Wireless has more problems, more security issues, as you can imagine. Um, so in this diagram, there are three stations, A, B, and C. First of all, you can think of Ethernet communication, Ethernet-based communication. So three computers are connected to the Ethernet. How your computer, how the network card of your computer or desktop recognized there is a signal. There is no collision. How do they know that? Along the signal, there is a along the Ethernet, there is a current. Current flows. which means energy, right? Current flows over the Ethernet. Similarly, wireless communication, carrier is nothing but the signal itself. It's nothing but energy. So it has amplitude, the amplitude and frequencies. And depending upon the energy can reach different distance. There's a current flows. Therefore, when 1 bit of data flows along the current, the energy required to carry 1 bit data is 18 to 20 milliamp. 18 to 20 milliamp. That much energy needs if you carry 1 bit. If there is a collision, data collision occurs, this current will increase, usually 23 microamp. If we are thinking of bit, then collision means 2 bits colliding. So 23 milliampere is flowing. So at each node here, by differentiating 18 from 23 or 23 from 18, understands there is a collision. This is a regular bit that I need to take. Okay. But while in wireless communication, we cannot do that, right? There's no current is flowing. So rather we need to control it by time, wait time. In other words, interframe space. Interframe space. Space is not the regional space, but time space, temporal space. 2 laptops needs to communicate. Well, not really needs to communicate. But if at some points, if they send the data together, then there's collision, right? But if they send data, same data, but there's some time interval, then there's no collision, right? This is the idea that we use. So I want you to read this, but instead this is a good example to save time. If you understand this, then all the slides that I skipped will be understood very easily. This is the example that we can practice here. So we assume interframe space, so-called IFS, and then also small, short IFS, so-called the SIFs, and then 2 types of coordination functions. Therefore, we have 2 different interframe spaces, PIFS and DIFS. So Um, Usually we have DCF function-based communications or protocols is running. Distributed coordination function-based communication, wireless communication is running. It is continually running. There's a contention period, which means so many one or more stations uh, wants to participate in this access. But wireless communication, all the communication, there is a channels, limited channels. Although we apply different multiplexing coding systems, still there's a limited. So time sharing is always needed. So a lot of protocols developed here. But at the same time, if there is a time critical, so peer coordination function is needed, then we need to set it up also. That is a contention-free period. But in any case, the algorithm applied in this way. Timer critical services use point allocation function, PCF, point coordination function, which is contention-free. Point coordinator allows only one station to access, because therefore there is no contention. Coordinator sends beacon frame to all stations, then uses a polling frame to allow a particular station to have a contention-free access, right? So this slide is talking about time-critical services, which is the PCF access. Now DCF, three variables used: contention windows, backoff counts, and network allocation vector. There's a frames: RTS, CTS, data frame, ACK frames, right? So if any of this is heard, then NAV is set to the duration of that frame. You have multiple, along that wireless communication, there are unknown stations available. Not unlimitedly many, but unknown. There's so many stations possible, right? So stations are also hearing, although there's a limited stations. If one sender and receiver, then two stations are occupying that sharing carrier sense. All others not involved, not participating at that time points. But all other stations can hear what they are doing. In other words, if you have one access point, then all stations, all your laptop can hear that access points. Although access points now at particular time along the particular channel communicating to a specific one station at a time, and all others still know. What they know is RTS, CTS. They can hear. They do not know, for example, data. right? This requires a lot of the encryption issues. But still they can hear. Every time each station hears, then NAV within that station, within that laptop needs to add the duration. If there is a RTS, then RTS has a limit, some duration. Okay. Already know. RTS packets can take, let's say, 2 microseconds. CTS can take 2 microseconds. Data frame may take 50 microseconds. Acknowledge maybe 2 microseconds. Somehow there is something, right? So each one knows that, oh, I want to wait this much, that much, because somebody is now using. So by listening it, I can allocate. I can increase and decrease my NAV. Station sense, each station, so all stations sense the media after NAV expires. If NAV, so one NAV over the one station expires, which means a complete communication, then everybody sends that. Okay, there's acknowledge it. Now, this is a time that I may use the channel. So everybody needs to wait, DIFS, time period. So by that time, one of those are picked and used. If medium is idle for DIFS, backoff is not already active, the station draws a random backoff count and sets a backoff timer. So anyone here, random process, says station 1 is next, and all others now idle. If medium becomes busy during backoff, the timer is stopped and new NAV is set. So, as I said, there's a random backoff. This is a sequence. And always if we want to communicate, then RTS, CTS, and data, finally, acknowledgement. And then another random backoff, RTS, CTS, data, acknowledgement. In between this, there's an inter-frame spaces. Interframe space this may be longer than all others here. All others here is short, right? SIFS. Channel contention resolved using backoff. Nodes choose a random backoff interval from 0 to CW stands for. Yeah, contention window. So during the contention, there's some time period, right? Okay, next 5 microseconds, contention. So you will be number 1, you will be number 2. Backoff and RTS, CTS handshake before transmission of data packets that we all already looked at. But this is very, very, very general and primitive, rough idea of 802.11 protocol. It still needs to improve. A lot of improvement already done, right? But needs to be more. Here is an example. Scenario is this. Scenario I wrote in the next slide, but here is what I can explain to you. Time runs. Okay, so this is time interval. Time 1, time 0, time 1, time 2, time. Oh no. Time. Oh, this is time 1. Time 1, 2, 3, 4, 5, 6, 7. So time runs, whatever time that is, right? And slot time is 1, so one slot here is 1 and 2, right? And contention windows is 5, minimum 5, which means contention, so 0 to 5 within this time windows. So minimum 5 can be more than this. 1 to 5, 1 to 6, 1 to whatever that is, right? And DIFS 3, PIFS 2, and SIFS 1. We assume that, right? Depending upon the wireless communication protocol device involved and all different kinds of factors. But let's say this is, simplify that, and this is the number. So at time, so and also we have 4 stations. 4 stations. And 1 channel. 4 stations wants to use 1 channel of the communication. At time 0, currently station 1 is using data. Okay. Before, along the same protocols, so we have previously RTS and also CTS packets, and therefore data packets. By looking at this, station 1 and station 4 are communicating. Station 1 send data to station 4. And finally, station 4 says acknowledgement. But if you look at this, along the time 0, still station 1 is sending data. Time 1, if I ask, for example, what's going on at time 1, then at time 1, station 1 is sending data. All others waiting. Time 2, at time 2, station 1 is still sending data. The arrow here, oh, station 2, can I? Station 3, can I? Station 4, can I? But they have to wait. So at time 3, station 1 completes the data send. And then wait, SIFS. SIFS is 1 time slot, so wait 1. And then acknowledge. Acknowledge takes time 1. So all the acknowledge, RTC, CTC takes time 1. Data, it depends, right? But SIFS in between should be 1 here. So after acknowledge, because this is done for 1 frame transmission done, right? Therefore, we have to apply DIFS, distribution interframe space. After this, still there is a contention period, which means everybody needs to compete. So wait. DIFS is 3, so we have to wait 3 time period. At time 8, then within this contention window, if it is 0 to 5, within this contention window, so 1, 2, 3, 4, 5, 0 to 5, it's minimum 5, so sometimes it's 6 or 7. So within this time period, station 2, 1, 2, 3, 4, if they are still waiting, they can randomly assigned. So at this, say time 9, station 3 is picked. So this guy has a shorter waiting time. So what it does is that he can RTS 2A and CTS. CTS should be come from here, right? So CTS here. So CTS received, and then data is sending. When data transmission completes, then acknowledgement, then SIFS, short interframe space, and after that acknowledgement received by station A, station 1. Then this is done. This is another packet transmission is done. So this is packet 1. This is a packet 2. And another packet transmission period comes. Before it comes, DIFS is needed. So 3 time slots needs to be wait. And then contention windows, along the contention windows, it may be picked up. Station 4 is picked up. Therefore, this guy needs to steer this station 2 continually back up. If you see here, station 2 continually back up. And do the same thing. Okay. No. Because they're all independent station. There's no queue. Well, there's the access point. Access points. For example, this CW. So random assignment is given by access points. So access points along each NAV. Each station has NAVs. So they know that, oh, this is a time. Let's say, oh, packet is done at this time point. Okay. So all the stations, its own NAV is now set to 0. So I want to access. Then along by the random number generation here, random number generation, 1 is picked up, and all others now backed up. There may be some other better algorithms developed, but this is rough and basic concept. Not just randomly reassigned to every station. Maybe there are some other mechanisms to be used. Yeah. Yeah, that is, yeah, queuing theory may be okay too. But we cannot say that always, because first in, first out is okay if we complete, for example, station 1 complete. Then station 1 will be out from the queue. But in this case, there's a packet. Station 1 wants to send, for example, 10 megabytes data. Each packet can contain half megabytes. Then it needs to send 20 packets. So sending 1 packet and wait and contention again. and sending another incantation again and again and again. This is not the best algorithm, but this is the basic algorithm. From this basic algorithms, a lot of research is going on, and a lot of researchers still wants to include security issues. This scenario, there's no security issues involved, as you can see. If we include the security issues, a lot more difficult. Think about that while you are driving back home and have a good sleep. Okay? This is done for this module. So all others, I think you can read it because we need to do encryption algorithm next week. Okay? See you next week.